To find the pH of a strong acid solution, the dissociation of the acid is nearly 100%. This means that the H3O plus concentration is much greater for the strong acid than it is for any contribution made by the water. So we can take and find the H3O plus concentration of the acid because it is equal to the concentration of the original acid solution. So finding our pH is going to be equal to the negative log of that original acid concentration. This allows us for any strong acid to find the pH easily. If we have a weak acid, we still have two sources that are contributing to the H3O plus concentration, one from water and one from the weak acid. But this does get a little more complicated because the acid does not dissociate 100%. Most of it stays as the acid molecule. So to calculate the H3O plus concentration, we have to solve an equilibrium problem for the reaction to figure out our H3O plus concentration. So finding the pH of a weak acid requires us to write the equation for the acid as it reacts with water and use that to help us prepare an ice table. We're going to complete the ice table given the initial concentration of the acid, and we do have to remember the stoichiometry. We're going to substitute into the expression for the equilibrium concentrations, or the Ka, and we're going to determine the H3O plus concentration by calculating the value of X. From there, we can calculate the pH. We're going to also check our answer to make sure that we've done the calculation properly. Let's look at an example. We're going to find the pH of a 0.2 molar nitrous acid solution. So we can look and see if our X, the decrease in X for our initial concentration, is small enough to be ignored. If we compare the original concentration, which is 0.20, to our Ka, which is 4.6 times 10 to the minus 4, and if we compare those numbers, we see that it is equal to 435. Because this is larger than 250, we're going to ignore the X, the subtraction of the X from our initial concentration. The homework uses a value greater than or equal to 1,000. So let's set up our ice table. We're looking at our original nitrous acid concentration and the concentration of each of the products. Water gets ignored because it is a liquid, and so it is not included in our equilibrium constant expression. So ice, initial change in equilibrium, our initial concentration of the acid is 0.200. The products are going to start out at 0 for the concentration. Because we have no coefficients, it's a coefficient of 1, so we're going to decrease the concentration by X and increase each of the products' concentration by X. We add the columns together, down the column, and we look at our equilibrium constant expression, again, products of the acid plus water divided by the reactants. Water is not included because it is a liquid. We can substitute in our values. So our Ka is 4.6 times 10 to the minus 4. The concentration of each of our products is X. And we're going to ignore the minus X because our value was larger than 250. So we put in the initial concentration of the acid. Rearranging this to get X by itself, get X squared. So to get X, we take the square root of both sides, and we find that X is equal to 9.6 times 10 to the minus third. Take the pH. To find the pH, it's the negative log of the H3O plus concentration, which is X, 0.96 times 10 to the minus 3. And we find that the pH is 2.02 for our nitrous acid with a concentration of 0.2 molar. Here's a practice for you to try. Pause the video and determine the pH. Our reaction is going to be nicotinic acid plus water gives us our polyatomic ion plus H3O plus. We set up our ice table. Again, we're not going to consider water. Our initial concentration of the nicotinic acid is 0.12 molar. 0 for our products. Our change is going to be minus X, plus X, plus X. We can determine if we need to include that X by comparing the initial concentration to our pKa, which gives us a value of 857. So we're going to ignore the minus X, or assume that it is negligible or insignificant. So we're going to set up our Ka expression. Products divided by reactants. We can substitute in our values. Divided by our initial concentration of the acid. So rearranging this, and take the square root of both sides, we get that X is equal to 4.1 times 10 to the minus 4, which is our H3O plus concentration. In order to find the pH, take the negative log of our H3O plus concentration, and we find that our pH is equal to 3.39. Okay, let's try another example. Let's find the pH for our acid. We'll compare our initial concentration to our Ka, and and we find that the value is 9. This is not large enough to ignore the X. So let's set up our reaction. Would be HClO2 plus water gives us ClO2 minus and H3O plus. We set up our ice table. We use our initial concentration. Water is not included because it's a liquid. Our products are going to be 0. Our change is minus X plus X plus X. And again, we cannot ignore our minus X because our Ka is too large. So we are going to have to use the quadratic equation for this problem. So our Ka is equal to X products over our reactants. And let's put in the Ka value. We're going to move the denominator to multiply. And we'll have to multiply through by our Ka. So when we do that, we end up and rearrange. We end up with 0 equals X squared plus 0.011 X minus 0.0011. Using our quadratic equation, minus 4AC all divided by 2A. Using and solving this problem, we have two possibilities. Our X is equal to 0.028 or negative 0.039. Because we can't have a negative concentration, it will not be that value. It'll be the positive value. So to find our pH, which is equal to X, the H3O plus concentration, pH is equal to a negative log of our H3O plus concentration, 0.028. So our pH equals 1.55. Here's a practice for you to try. See if you can determine the Ka of the nicotinic acid. We're given the pH and our initial concentration. Pause the video to determine your results. We are going to have to find the concentration of the H3O plus. So we're going to take the pH is equal to the negative log of our H3O plus concentration. To undo this, we're going to take 10, our H3O plus concentration, is equal to 10 raised to the negative pH, in this case 3.40. So we find that if we take that value, we get 3.98. If we round that to significant figures, which we have 2, it's going to be 4.0 times 10 to the negative 4th. for our H3O plus concentration. Yep. So if we look at our Ka expression, and I do want to point out that frequently you'll see acids abbreviated as HA. So H is our hydrogen, A is the rest of that polyatomic ion. So A is just standing in for that. If we look at our ICE table, our initial concentration is 0.012. Our change, our equilibrium concentration of the H3O plus is going to be 4.0 times 10 to the minus 4. This is the same concentration as the A minus, which is also the change in our concentration. So our change is going to be a negative 4.0 times 10 to the minus 4. Okay, which is actually too small to be significant. So if we do that subtraction, when we round to two significant figures, we get the same value back of 0.012. So we're going to plug that into our Ka expression. So our A minus times our H3O plus concentration over our initial concentration of the acid we find that the Ka value for this particular acid is 1.3 times 10 to the negative fifth. So this is our equilibrium constant for nicotinic acid.